So I will talk about the title, the onset of magnetic reconnection, tearing instability current sheet with a guide field. So it's a 3D reconnection case. So this work was done together with my co-workers, James Leake, he's now at NASA, Goddard, Klimchuk, and Carl McNisnik, that's now at NRL. So the background for this problem comes from looking at the Poynting flux at the solar surface. So the photosphere will create a motion that will create a Poynting flux that you can describe in the fashion here when you have a shear, a flow and magnetic field. It will start shearing up the field and create a Poynting flux describing it down left. And this is basically putting energy into the solar atmosphere. So for this project and what I'm talking about, we are focusing on the Poynting flux that will contribute to the free energy in the system. So not be ignoring the Poynting flux that will go into the potential fields, and we're also ignoring here wave propagation and wave interaction and this type of stuff from the photosphere. So we're interested only in the shearing up of fields and how this can lead to reconnection that will release energy into the corona. So basically, this is the setup we are interested in. We're looking at the loop. And for a loop, the energy from a reconnection is dependent on the magnitude of the reconnected magnetic field components. So to get more energy, we need more magnetic field that can reconnect. And the buildup of the field component depends on how fast it will reconnect. So we get it to shear up more, we get more energy out of it. And for this work, we concentrated on the loop architecture and their dynamics for the current sheet generated in them, for the closed field line region. So one of the issues is when you have a loop, you have a lot of strands, and this generates thousands of current sheets. What happens with those current sheets? How will they develop with time? Here's a picture from Parker's paper, if you remember, of what possible interaction scenarios there is. So this is a background for our work when we're looking at the 3D reconnection case. So in opposite to most other work that has been done in the field, we have not worked with one code because we are very much interested in what is the value of the energy released. That means we cannot accept a numerical error. We don't know exactly how much it's influenced our solutions. So making sure that the solution we have no real artifact we don't understand, we have run into multiple codes with different schemes. So one of the big ones is the BATS-RS code from the University of Michigan, part of the space weather modeling framework that I've been working on earlier. We're also working with the ARMS code from Rick DeVore at NASA Goddard. And the two last one here is the one we are using most the late level present results from. That is the Layer 3D code from England, Adrian group, and the new GAMERA code we are developing at APL. So GAMERA stands for Grid Agnostic MHD for Extended Research Applications. So it's mostly developed for, as most people think of it, as an inheritance from LFM code and developed for magnetospheric. But the general principle behind it and the main solver is general purpose multi-fluid or single fluids. So I'm just presenting short these two codes because they're very different. So the layer 3D code is a viscoresistive 3D MHD code solving using a Lagrangian remap approach. That means it's not in Euler and solar. It's using basically, you can think of it as a fluid particles to move like a Lagrangian on the grid. So it has no the same restrictions moving across the grid planes. So it gives different properties. It's not in the conserved form. Here you can see the equation we are solving for it. It has also more things used. The black is what we're basically using at this moment, just standard resistivity and the pure MHD equation, but there's also influenced field-aligned thermodynamics and space-aligned, also partial ionization for chromospheric conditions. So this will be extensively used by James Leake for his research. The other code, and the one I'm also a co-developer of, is GAMERA code. So it's a finite volume method using up to 8-order reconstruction. So it gave us a lot of help in regards to gradients and gave also the good properties of the code. So what is implemented today is a standard resistor as MHD. We have also gravity, and we also have a resistive diffuse magnetic field. We have not included the ohmic heating term. I'll come back to that why later. So this code is also ready for multi-fluid description. So this will expand in the future for also do more multi-fluid. So it's very proper for the magnetospheric problems we're using it for. So I can show some examples, test runs with the GAMERA 3D. It's using also an analytical grid description, so you can do any kind of warping of the grids you want. To the left here, you have the 3D blast wave example through a grid. And you can see here, this is, the lines give you basic, I think it's every 10th grid line, and see how they warp around and how it interacts with the blast wave. And if you see clearly, in the end here, we're getting instabilities that are physical, but in the initial case, you see no real effects from the warping of the grid. So good possibility. Down to the right, we have just a convection test to see how it deforms with time. And this famous time vortex to the right. You can even see the reconnection current sheet. But this is done with numerical resistivity, so it's not really controlled. So this is a code that's in the development, and we also hope to work with people here to continue developing this code for the solar purposes. So what I want to talk about, I will talk about, is basically 3D reconnection. And in 3D, we have the standard reduction equation. But we have now just a constant resistivity to make life very simple. That if you take a linearized system of equations, and here we have the x-axis, this is a typical example of initial conditions. You have an x magnetic field in x across z, across y, I mean. So x vertical is y. Then we can look at the generated magnetic field. Can be written in linearized form here. So the way we can break the frozen field conditions is when the resistivity started dominating the expressions. Otherwise, this solution will be convected faster than diffuse. So to get our reconnection condition going, we need the resistivity line to dominate the solution of it. The resonance surface will be basically when this convecting term equals to 0. In 2D, this is basically when you have in Fourier components the k vector going to 0. Or the system we go, you can also look at this, but the L's of the system of the waves are interesting, goes to infinite. So this term doesn't exist in 2D, it disappeared, and we only have that, and we will only have a reconnection in the middle of the current sheet, as illustrated on top here. You get the classical, more like X point with a central current sheet in the middle, and the Y-shaped jets out on each side, or jet like the Sweet Park has the same form. But in 3D, we have more solution for getting the B0 div to be 0, or we call it later the k dot b. And that is when this condition is fulfilled. So you see we have discrete numbers where this condition will be fulfilled. And this one will be a function of y. So when you're moving across, can be a function of y. So when you move around, this condition can change. That means you no longer want single points where reconnection or resistive tearing can appear. But you have now a bunch of infinite layers, depends on your geometry of the current sheet, that will decide where your reconnection can happen and which speed it will happen at. So this is the main course of this talk will be about the issues surrounding that. Any questions? So in the classic case of the Sweet-Parker, that's been the leading description today, we all know that we have the magnetic reconnection and quartic magnetic ending into the thermal energy of the plasma. So basically, this will happen because of the reconnection in the center of the current sheet. The main issue here is that Lindquist number is what describe well the reconnection of the current sheet. And it's described by the length of the current sheet, the alpha speed of it, basically the inflows, and the magnetic diffusivity, D. So for typical coronal conditions, this can be up to 10 to the 10th, or even higher in some cases. In most of our interest or problem, 10 to the 10th is a good number. For these cases, they've shown that Sweet-Parker will give you a reconnection rate that's too low to anything that's observed. Everything you observe today is basically a much smaller scale, time scale, than what Sweet-Parker predicts from his growth rate. So if you look at the growth rate, gamma tau, it goes to 1 of square root of the Lindquist number. The only thing is, that you always should be aware of when you talk about Sweet-Parker, is that the aspect ratio is also described as a part of the Lindquist number. So there's a lock on that. So this again raised a couple of papers that have shown that we can get much larger growth rate than predicted by Sweet-Parker in their original text. And Lorine 2007 showed what they now call the plasmoid instability. So in this case, you get a much more faster reconnection rate among them because you get multiple reconnection points. So you get more points that we can convert energy. And also, you change phases there. But all this comes back to the relation when you get larger Lindquist numbers, you basically change your tearing mode of the system to go much faster. So it was shown by Baccia and others that then you get a much faster growth rate just because of this relation between the width of the current sheet and the Sweet-Parker rate. And this points a little bit back to the Sweet-Parker. Current sheet is not necessarily a good description of the current sheet we're operating on in the solar physics. One issue has come back is that Sweet-Parker, most of his models, they predict a static reconnection scenario. And this is also never really the case in solar atmosphere. On the timescales of most of the large-scale phenomena, the life expectancy of current sheet can be pretty short for flares in CME. That means what needs to also be understood better is the interaction of dynamically changing current sheet. And both in regard to thickening and thinning of them. So one example here, the picture taken at Wuhan 2070 paper for 2D reconnection, that you can see the different phases and basically how we get into the fast reconnection scheme with a straightforward Sweet-Parker scheme. So explain the figures, the top plot here show the current density. So the top half is the current, and lower half is the flows in X along the current sheet. So this is a Sweet-Parker sheet, so it means we have outflow in both ends. So that's why you see a negative flow and a positive flow in the two parts of the figures. So in top panels, we see the initial condition where the tearing mode is growing in the system. We have an initial current sheet, and you can see outlined in red the mode of the tearing growing in time. After a short time after this, we basically go into a plasma stage that the tearing mode is going past the nonlinear stage. And we now have discrete plasmoids form. And between each plasmoid, we have now a new current sheet. We start again the same process of tearing mode happening. But this is very much a dynamical current sheet. As the plasma is starting moving in and out of along the current sheet, we can get longer and thinner and shorter current sheets. So now it's getting very much dynamical. This second to last picture show a little bit later when the reconnection rate is max. And now we can see that we have a whole cascade of plasmoids of different sizes. And we can see that we have a lot of growth of new plasmoids in between the different current sheets, generate more flux conversion. And in the end, we have a saturated system, basically reaching a steady state in the reconnection rate. Yeah.
What determines the steady state separation between?
Basically, when you are plotting out the reconnection rate as time as an integrated system, you can see it peaks up and then it flattens out in many of these cases. And that is often limited by how you set up your simulation. Yeah.
But there's no characteristic scaling between those plasmoids?
Initially, yes, because it's set up by the Thierry model. The Thierry model has set value. But as soon as you get beyond the linear phase of the Thierry model, you will basically have a multi-component K-space for waves in here, in the middle of the current sheet. So in that case, how these are moving, remember the magnetic field sounding here is tilting a little bit. So these will move out differently with different velocities to each other. That means that the new generated current sheet between the plasmoids have not a set K value. So each current sheet has a separate Thierry mode and dominating K mode. But when you have a dynamical changing current sheet, that K mode is changing continuously in time. That means you will, for all sets of current sheet that is dynamically changing, it will grow in many different K modes. So it can at any time will have plasma at different scale. It can generate plasma at different scales. So the top one is the current. So they're split in two. So it's basically symmetric. No, so the color here, that field is velocity in x, also along the current sheet, and the blue and red is the currents, and green orange is the velocities. So you basically see a more or less homogeneous current sheet, but you see is one side is flowing out on this side, and the other side, orange is going out on the left. So you're just illustrating the current at the same time. So for our case, we're using 3D simulation, but we're interested in loops. We are inside the closed corona. So we basically, what we do is doing the closed corona setup, a loop, where we can have shearing of the foot points. And we do as Parker and others and say the loop bending is not the important part. It is, we can simplify it with stretching out into a slab, 3D slab. And we just change the gravity to put it up for simplifying the system. For the current sheet, we are using close to the Harris type. So the B1 tangent hyperbolicus is the same as a Harris current sheet, but to make it fully periodic in a smaller space, to not getting issues with boundary conditions, we have an enveloping cosine to make it periodic on boundaries. This has shown to have very little effect of what is really happening inside the central current sheet. And we do a force field configuration with fully periodic system here. So we can set just BC as a function of BX. So here's the typical values for the runs we have done. So the background field is like 10 Gauss. There's a vertical field. The horizontal reconnecting one is peaking at 3.6 Gauss, 10 to 5. We start around 500,000 Kelvin. Plasma, atom velocity 8 10 to 5th. The width of this current shift is set to 0.5 megameter. The total dimensional in X in the 2D runs is 100 megameters. So you get an aspect ratio of 200. We have quite high magnetic diffusion, and this is to make sure that there's more than anything we can expect numerically in 3D cases. So all our case runs is centered on 3D, so all parameters are centered on what can be fulfilled with 3D runs. So the thing here is that we have still quite a low Lundquist number or high resistivity, 10 to 7. So this is basically giving us 10 to 7, but what should be 10 to 11. So this gives us some drawback to comparing to the real solar case. So also we're using a population of lower frequency component of the velocity in y to set, or the x, to set a background noise to have the growth grow out from. So this is basically how this looks out. This is an example where we do shearing on the boundaries. In most of the cases I will show, we just keep it static on boundaries. Here we have a static boundary, shear boundary, and we get these tilted fields that is periodic, and we have a central current sheet in red here, and we have the magnetic field in blue here. So this can generate either with static, setting up statically for initial, or with shearing up and reconnecting Harris type of current sheets. So what I will talk about is the issues from using higher resistivity in the models than it was in the solar case. So one case, what we did to illustrate this is taking the two planes I showed before, put up a sinusoidal shearing, and run it to steady state. That means when you're shearing up the field to the point where the diffusion breaks down as much at the same speed as what you're shearing up the field. So you get a steady state solution. And we did a case with a low and one with high magnetic diffusion, so a factor of 10 between them. So this is also 50 by 50, 50 by, okay, error that should be 50 megameters. So we take the center of our box, 3D. And what you can see here is that this is the log temperature. With lower shear, we get basically almost twice the velocity, twice the temperature of the plasma. And the shearing angle we get max is basically 20 degrees. 10 times higher the resistivity, we get down to 3 degrees and just a little bit of a 500,000 degree Kelvin. So that means when we have increasing resistivity, if you look at the ohmic heating part of the equation set, we are expecting lower heating than we would observe in the real corona. The second part of the ohmic heating is looking at the 2D reconnection problem with and without ohmic heating. So it's basically the same setup as I showed initially. And here you can see we have ohmic heating in the center of the current sheet, what we see looking here as the density, and the velocity inflow and outflow into the current sheet. So that is the rate. If you can see, the heating is so large in central current sheet that basically send the outflow out of the central current sheet in opposite direction of the inflow generated by the tearing mode. Instability, basically limiting our reconnection rate drastically. If you remove the ohmic heating, we get back to what we expected from the theory of the modes and how the inflow pattern should look for tearing and the density. So from those two examples, with the drawback with keeping the ohmic heating inside the equation set, we decided to remove it from the equation. So in the example I show you now, you have an express resistivity for diffusion of the magnetic field, but we have no ohmic heating. So we have a net loss of energy in the system. But we are also in a low beta plasma, around 10%, no, 1%. So there shouldn't be too much implication of that on the plasma itself, if you look at the surrounding plasma. So this is an example from layer 3D. The top panel is the JX. Mid-plane is the V velocity along the current sheet, and the bottom level bottle plot is a BY, the generated magnetic field. Here you can see the modes growing up, and when they grow harder, we get stretching out of magnetic fields. Of the current sheet, and we generate a new level of tearing modes. So you can rerunning here. You can see this initially, because of the way the scheme is built, we have a high fluctuation rate in the beginning that stabilizes statistically. And here you have the tearing mode going from a nonlinear stage, generate strong current shift between new tearing modes with generate inside area, and we can say now new plasma being formed. So it's no good to try to do this if you can't verify what you're doing. So what we did was taking runs like a previous run, look at the FRE component of velocity and how they grows in time. So in this example, we are taking the velocity in the middle of current sheet. Is a 2D example, not oblique modes, just parallel. So we can just the center mode. And we look at how the max velocity, the K values, amplitude of the Fourier component. The Fourier component of velocity in center of current sheet grows in time, and compare with the linear theory. So you can see here the straight line is the theoretical prediction by bounding layer theory. And the fastest growing moment should be 4.0. But because we have some diffusion in the system, there is a change for what the dominating mode in the system is. So it goes from 4.0 here to 5.0 during the simulation time. So at any point in the end of simulation, there's two wave numbers that it's quite dominating, and there's a 4 and 5. That means you have four wave periods over the box and 5 periods over the box. The initial fluctuation you can see here is from the numerical scheme. It's statistical, and you can see it's as the wave grows stronger, it grows out of the noise, and then goes flat to follow the theoretical prediction very well. So this is capturing the linear part of the growth, and that is what we can match with theory. After that, it's very hard to start matching up with theory because the dynamics of the current sheet is so much stronger. So it's no good theory for it. So if you come back to the 3D case, so here is a 3D current sheet. So what is the difference? Yeah, the main difference is K dot B equals 0, or the oblique modes. So now we have a huge amount of what's called resonance surface and many location in the current sheet. So this is taken from one of the runs we did in 3D, giving you basically the center of the active region of the current sheet. And you can see here we have these diagonal modes going through the system. So basically they have three periods along the current sheet and one in Z. So we call it 3-1. And you can see it's going one side goes from right to left, and other backside is go from left to right because of symmetry in the current sheet. But you can also see the central parallel mode as a strong, more or less straight line. If you look very closely here, you can also see that they're starting to interact, and some of the lines are starting bending weakly from reconnection, and the interaction between the oblique and the tearing mode. If you manage to look at the end here, the projector is not the best. You can even see the current sheet here that forms because of the interaction between the oblique modes and the parallel modes in the center is starting to form in non-parallel fashion. So you're starting to breaking up a lot of symmetries. And this is what also been observed by others, is that when you do this 3D reconnection, you can get the self-generated turbulence. But now we come back to the main issue, is that to get a proper description of self-described turbulence is that then you have to also resolve all the current sheet and all the oblique modes that is related to your system. And that back again, since it's dependence on the K, that means it's a geometrical dependence on the current sheet on which oblique modes you have to resolve. So when we then again have a dynamically changing current sheet as a CME, flare sheet, and so on, it will be a very highly dynamical system that is not a single mode in the same sense. So one of the issues we want to look into this is because now we have tilted field regions starting interaction, is that how will these build up and making kinking possible for a new generated flux rope and so on, and get kinko-stable flux ropes that again can generate more energy, as shown by Daldorff papers earlier. One of the things that if you follow linear theory is that the parallel mode is always the fastest growing one. And the closer the oblique mode is to the parallel mode, the longer the depth of how long the current sheet is, as in Z direction, in the third dimension, the closer this growth rate in linear theory is coming to parallel mode. So it means that for very short current sheets, you will get a very high dominance from linear theory of the parallel mode, but as you start stretching your current sheet, you will get more and more interaction for the oblique modes. But this also very much depends on how well resolved you have your system. So one example of that is what I have here to the left, was on our very early runs we did in 3D with a highly shared field. And you can see here the two sides of reconnection starting going around each other as two interaction of two oblique modes. And this was basically one of the reasons why we started to really look close into the current sheets, was that this is very much not what you expect. And we found out in this case we had under-resolved the parallel mode in the case, for doing this reconnection. It's a good illustration of the type of turbulence you expect from oblique reconnection cases, where you get the high inertial twisting, so fields that come up here, come in and behind and come out on the other side, or just twist around and coming out, generating new flux ropes. This is compared also to so this is a much later stage. So this is the earlier stage you can compare with earlier, where you can very well separate the parallel straight mode from the oblique modes on the two sides. So that is basically the state we are. This is an ongoing project. We hope worked on this in 2 years to make sure we get out all numerical effects. So also this project is understanding the rapid onset of magnetic reconnection in dynamic forming current sheet in chromospheric corona. So with time we need to include more effects, especially like line tying issue studied by Hood and all others, and so on, to see how this will interfere with reconnection. Also, when you get a different resistivity in the chromosphere for corona, where is most likely where is the most likely to observe the reconnection region? How far will it be able to share it in the different regions? So far, we have concentrated the picture show you is pure corona, lower corona current sheets. But the one issue we'll go to is go through the whole loop to how it will interact. Yeah, and also then go into the dynamical current sheet problem that we observe when you have flare and all this dynamical system where you're pushing magnetic fields together. You have a dynamic changing current sheet to change also its not only the width of the current sheet and strength of magnetic fields, the gradient of it, but also as you stretch it to change its geometry, to change new modes, oblique modes can be generated. Also parallel modes can change if you stretch it further. So yeah. So the main conclusion I will present here is that in 3D reconnection, we have a whole lot more current sheets to think of. It's no longer just a parallel mode. We have a whole width or area where reconnection can happen and interacting, generating more kind of turbulent type of current sheets. So reconnection data sheet has a strong dependence on geometry. Remember that. Possible solution include existing oblique modes. So that is one of the big one for us, is that as you change the geometry, new modes can appear and disappear. And you can generate stronger, as if you change it dynamically, you will get, instead of one single mode, as I showed earlier for the pure sweet Parker current sheet, you get one tearing mode. But in the dynamical one, multiple modes will grow at more or less the same strength simultaneously, giving very much more dynamics. And for us that do numerical models, you need a very well-resolved current sheet to capture this. So this is one of the issues we want to go back to when we have a better understanding how evolution is of the correct current sheet as physical, to see how can we take this knowledge and put back into our global models. Because in global models of CME or flux robes eruption, you can never go down to meter scales or kilometer scales for every time you have a single current sheet. So trying to interfere this, what information we can get back and say about reconnection in a real corona case. On time scales, say how much more higher temperature should you expect in reconnection region will have, and then what you get produced, and so on. And this can have implication for spectroscopy, where you need to know the exact density and temperature that will be emitting the plasma. But because in these low resolution runs, you basically get a very diffused out process. And that means, as I showed you from Ohmic heating example, you get much lower temperature than you should in the real case. Okay, thank you.
So you showed us the reconnection current sheet from that was an LHD model you said?
Which this one or?
No, before the one with anti-symmetric field right here, for example. So typically you see that also in big simulations, which is on particle scales. And this is an LHD model, so these are expected to be fluid scales. The reconnection that's ongoing, right? The islands that form the plasmids, they look rather similar. So I'm just wondering why on different scales we see a similar image or a similar current sheet.
I think you need to go back to basically it's the cybermetric field description. So as long as you have a current sheet, if you go back to tearing mode theory, we basically have a current sheet. How does it go unstable? And you go into the Ampere's laws, Maxwell equations. I think basically comes from Maxwell equations, that as type of instability of the wave generation. So the wave patterns come from Maxwell equation when you have this type of current sheet. And the second thing is that if you look at interaction between islands, so you can see here, we get this island growing up and they start an interaction and spread out and do reconnect, merge. This is very different in kinetic simulation because you get, when they get these emerging, you get electrical fields, electrostatics involved in it, very small scale, position and all the other forces that make them more repelling than for the MHD case. So I think you need to be very careful there. I'm not an expert on this kinetical side of it, but it looks the same, but you cannot draw the same conclusion for everything. Because I know for a lot of these dynamical plasmoids, in the fluid description, we have lost so much that it's different physics than what you see when you do island coalescence in the kinetical description. Yeah. So all of my simulation is a low beta. This is high beta. This is a beta of 6. Yeah, that is low beta. That is a coronal collision. it's happening in the current sheet. So you're dumping so much heat because of the high resistivity you're using in numerical scheme. So this is a little bit different. So if you're using numerical resistivity, you have no control over resistivity. You don't really know which mode will pop up because it's deciding of how well your reconstruction fit also the shape, real shape function and so on. So you lost a lot of physics, but you're putting it into basically a diffusion operator. You say, when reconnection happens in this area, numerical diffusion, make an approximation to it. And that is fine. That's nothing bad about that. If you solve that conservatively, or if you put back the numerical lost energy, then you can get into the case where you're putting so much energy that should have got into magnetic field and jets into local heating. So you're heating up the plasma instead of moving it away from that area. And that, again, can push back the reconnection rate and stop the, also reduce the reconnection speed. So, yeah, this case here.
One question for your stretched out closed loop model. So from the equation, I believe the magnetic field, the absolute value of the magnetic field is constant along the loop, right? Is that correct?
Yeah, also initial condition, yes. And then you share it.
Yeah. So I think in reality one should maybe scale the magnetic field because in the coronal path the magnetic field is expected to be lower. So one could maybe make the initial condition a bit more realistic in that sense.
Yeah, also that is things to come in doing that. But if you do also a sharing with a proper atmosphere, you get some of the same effects.